Hey, how's it going? I want to continue with this series of videos, the last few episodes where I have been talking about example circuits and problems. But right now, I think what I'm going to do is take a quick detour and talk a little bit about resistors in particular before I start working with circuits with resistors in them. So this video I want to do ideally two quick examples where I talk about energy calculation or delivery to resistors. So like I said, I have two quick examples, so depending on how long the first one takes, I'll do the second. So let me jump right into it. I'm going to set up a scenario and then pose a question. Okay, here we go. This is the scenario, and yeah, I know this looks trivially simple, but that's because the point is this isn't a circuit analysis problem. This is a resistor analysis problem. So I'm drawing a single resistor with leads like this and these little dots going off into the ether, indicating that this is connected to some circuit, but it doesn't matter. All that we care about is there's this current coming in and entering this resistor, and then we're going to pose a question, which is, what is the energy consumed or delivered to this resistor to R between, well, we'll say from time equals 0 to infinity. So this time interval, 0 to infinity, like that. And we're going to give that we know IR if the current in the resistor is a function of time given by 10 e to the minus 2t amps. And the first thing you might be thinking is, well, hang on, we know very easily how to calculate the power in this resistance, given that automatically, hey, we know the resistance and we know the current, so therefore we have power. And you could also calculate a voltage based on this current and this resistance, but just with the current and the resistance alone, that's enough for us to calculate power. And if you remember, I forget which video it was, but it was several videos back now where I discuss voltage, current, power, and energy, and how you can get energy from power. And think about for a second the units of power. Power is watts, also known as joules per second. So power is a rate. It's energy transfer. It's energy per unit time is what a watt is. So let me write that out. A watt is joules per second. That's power is energy per unit time. Okay, so given that we have a current and a resistance, and we have an idea about how we might calculate this power, we know that we can integrate this power over some time interval to calculate or add up all the energy over that interval of time that enters or is delivered to that resistor, or how much energy is consumed in that resistance. We start by recalling the fact that one of the ways we can calculate power in a resistance is using the value of its resistance and its current. And we know that formula to be that P sub R, power in the resistance as a function of time, would be equal to the current in that resistance as a function of time, and this is squared times the resistance itself. So this is just a slightly more detailed or sophisticated rendition of the simplest way to write this is just P equals I squared R. That's all this is. I'm just saying the current in this case happens to be a function of time. Therefore, the power is a function of time. So this is just P equals I squared R. The power in this resistor is its current squared times its resistance. And if you look at this, we have the current as a function of time. It's given in this problem. And then using this expression, we therefore have the power as a function of time. So let's go ahead and write this out fully. In this case, P sub R of t equals, it's 10 e to the minus 2t squared, and in this case we have 10 ohms here, just like that. So I'll simplify just by stepping through all of this. This will be 1,000, and okay, and the units here are watts. I'm leaving this off just for quickness here. 1,000 e to the minus 4t. And that's our power as a function of time. Now we remember the general fact that the energy in this resistance is equal to the time integral of the power in that resistance. And so in this specific case, this is equal to the integral from 0 to infinity. This is as time starts at reference 0 and just chugs along to infinity, over this function 1,000 e to the minus 4t dt. Now to step through a quick integration here, I'm assuming you can follow along with this. What we're going to have is minus 250 e to the minus 4t, and this is all evaluated with respect to 0 and infinity, giving us, brackets here, this is when you evaluate at infinity, you're going to get 0, and then you subtract the evaluation at 0, which gives you minus 250. And if you complete this algebra, what you get here is 250. And if you look back and remember that we just did an energy calculation, we know here that the units are joules. And now look back at our initial question. What we had here is what is the energy delivered to the resistance across this time interval, given that we have this current as a function of time entering the resistor, and the resistor is 10 ohms? Well, the answer is it's 250 joules. And you might be thinking, okay, well, does this make sense? How can it even be a bounded number? And it does make sense that it is, well, because we look across this interval, infinite time, how can this be a finite number? And that manifests itself in the fact that we just know how this function looks. And if you know how this decaying exponential behaves with respect to the x-axis, you know that at least from t equals 0 to infinity, it is bounded. It does decay off into nothing as we approach infinity. So we know we can have a definite integral solution to this question. And so that is one example, and I don't think I've gone too long here, so I think I'm going to do another. Okay, so I've set up a near identical scenario. This is another resistor connected to some circuit that we don't care about. We're just going to analyze the energy in this resistor depending upon its resistance and, in this case, the voltage rather than the current. So we have this VR here across the resistor, and I'm going to give, well, first I guess I'll ask the question again. Energy in R across time interval, I will say this is bounded between 0 and 2 seconds. So what is the energy in the resistor, the total energy delivered across a 2-second interval, given that that voltage, VR, and it's another function of time, equals, in this case, it's going to be oscillatory, or it's going to have a frequency. I'm using a sinusoid here. This is 24 cosine 2 pi t. And here, I'm going to use a very similar approach. So again, we know that we have a voltage and a resistance. So we know very quickly from what we've learned so far that we can calculate the power in this resistor. And then, just like I did in the previous example, given that we know the power and we have some time interval, we can integrate across it and count or add up with respect to time how much energy is delivered to this resistance. So let me first write the form with which we would calculate the power in this resistance, given the fact that we have a voltage. So this would be PR of t equals V R of t squared over R. And here, again, this is just P equals V squared over R. This is just power in a resistance, and in this case, the voltage is a time function, so our power is a time function. And now, let me write this out. I'm going to start, let me start with the integral. So we're going to integrate. We know that the total energy in the resistor across this time integral is given by Okay, so the integral over the interval of the power, that should be a p, of the power function, let me try and make that clear, the power function of time, which in this case, I'm going to say, I'll do 1 over r integral from 0 to 2 of v r of t squared dt. So we have a 12 ohm resistor, again integrated over 0 to 2. And now if we square this function here, we have 24 squared cosine squared 2 pi t dt. Okay, now I'm just going to step through this algebra quickly to get us one nice constant number out front. So this is 48 times the integral over 2 seconds of the square of cosine 2 pi t. And now if you have a calculus background, this is where you know the easiest way to integrate this cosine function is just to apply a trig identity here for cosine squared. So I'm just going to introduce that where we have that. So cosine squared just so happens to be equal to 1/2 times 1 plus cosine of 2 angle. So let me go ahead and write that out. So we have 24 integral from 0 to 2, 1 plus cosine of 4 pi t dt. Okay, now I'm finally poised to actually evaluate the antiderivative here. Let me go ahead and write this. So now we have 24, and then inside here it's times t plus 1 over 4 pi sine 4 pi t, and this whole thing is evaluated across 0 to 2, which in this case, as I write this out, will give us 24 times, now if we evaluate at 2, this gives us 2 plus, well, okay, then sine of 8 pi, that's just 0, so this is 2 plus 0, and then we subtract the evaluation at 0, which also is just going to give us 0, and sine of 0 is 0, so then we have 0 plus 0, and then what we get here is 48, and remember this is energy, and we integrated watts, so we're going to get joules here. Okay, so that is the energy delivered to this resistor over a 2-second interval, given that you have this voltage function of time. And this is a sinusoid with some frequency and some amplitude here. And like I described with the case of that current in the last example, where that current was a decaying exponential, you can see how that power, or rather that energy, adds up over time and is bounded. In this case, the only reason we have a bounded energy here is because we capped this time at some reasonable value here. This is 2 seconds. If we had let this go to infinity, we would have infinite energy here, because this is just a sinusoid. It's oscillating and delivering current forever. Now this is actually an interesting moment where I can stop and maybe allude to something that I'll talk about in another video. If you think about what this voltage function looks like in time, you might be kind of concerned about how the current or voltage polarities make sense with our rules for power consumption in resistors. And what I'm talking about, if I can just make a quick drawing here on the axis. So without getting into specific details, this is a sinusoid, and we know this looks like this, dot, dot, dot forever, where this is 0 amplitude, this is some positive amplitude, and this is some negative amplitude. So what does it mean to have a sinusoidal voltage across this resistance? It actually means that the voltage is not only changing in amplitude, but we get to certain points where it goes negative, which means that it actually changes polarity with respect to how I've drawn it here. So this polarity is changing back and forth and back and forth. And then you might be asking yourself, well, hang on, if that voltage polarity is changing across that resistor, what does that do to our power calculation? Because all of a sudden we have negative V, positive V, negative V, and we know that depending on the polarity of this resistance, the current is going in a different direction. And that means that, so if the current's changing direction, what does that do to our power calculation? And what you need to realize is that, of course, this is just a resistor. It's a passive element. It can only consume power. So no matter what happens, no matter what direction this voltage polarity goes, it's consuming power. And you realize that the current direction changes with the voltage polarity. So at least our convention for the math always works out. But regardless, it can still get kind of difficult to think about when you start doing these integrals with sinusoids. This is, a relatively easy one. But what if you didn't want to do this? What if you didn't want to write out, this list of math or the several lines of calculus just to get this simple answer here? You just got a voltage and a resistor, and you just want this one number, and it took me 3 lines of calculus. If I don't want to do that, we can use a very interesting property of sinusoids that I think I'll make an entire video on this. But basically, if you already know what I'm talking about, I'm going to use the RMS value of this sinusoid to essentially do this calculation instantly. And let me write out what I'm talking about. So basically, RMS is a type of average that allows you to ignore the fact that the polarities are changing, and it essentially will convert the value, the amplitude of this sinusoid, into some equivalent, slightly smaller value that you could apply to this circuit, and essentially pretend that instead of a sinusoid here, you have some DC voltage. That if that DC voltage were applied in the place of this sinusoid, you would actually deliver the same power over some averaged amount of time, or the same energy to this resistance. So what I mean by RMS is there's some DC voltage that I could be applying to this resistor instead of this AC sinusoid, and you would never know. It would deliver the same power, the same energy. And what that boils down to, and I'm just going to do this for the sake of this problem so I can check my work here, and if you know what I'm talking about, great. If you don't, I'll make a video on it. But essentially the RMS value of this voltage, so I'll say V RMS, is the amplitude of the sinusoid 24 divided by root 2. And now if I take the power, which I can just use VRMS and square it and then divide by the resistance, we'll see what I get. 24 divided by root 2 squared divided by 12 equals 24 watts, and sorry, this is power here. So VRMS gives you this, and then power is VRMS squared divided by the resistance, 12. That gives you 24 watts. And guess what? What happens if you deliver 24 watts over 2 seconds? You get an energy in the resistor of 48 joules. That's 24 watts times 2, 24 watts over 2 seconds, 48 joules. So this RMS technique is very powerful. If you don't know what this is, you're wondering where the hell I got this root 2. And I think this is a really important concept that a lot of electrical engineers don't understand, or a lot of students struggle with in the beginning. So I'll definitely make a video on this. Anyway, point being, I hope these 2 examples of energy calculations in resistors were helpful. I may or may not do another video like this, but I think what's coming is the next several videos are going to be more circuit analysis, KCL, KVL oriented, but I'm going to start using actual resistors in them rather than just my generic circuit element symbols. So I hope this was helpful. I hope you enjoyed. Let me know if there's anything I can do to improve, and otherwise, have a great day.